Okay, so hello everybody. Welcome back to the class, second class on polymer physics. So what we shall start today is with a short video which shall emphasize the extremely strange flow properties, the so-called viscoelastic flow properties of polymeric fluids. So let's first see the video. You can also find it in my webpage. And this is not a video from me. You can find it in a YouTube. And what we shall see is basically you have a polymeric fluid, uh, and so you'll see that it will flow, but the constituent of this fluid is not atomistic particles like you have water, but extremely long chain molecules which are entangled with each other. And it is, you can see that this polyethylene glycol. And once a fluid starts flowing, what it will do is basically, since they're entangled with each other, there are also elastic properties and it will pull other fluids uh, down. So what is done here, if you see, is that you have just tilted the this picture a bit, and after that the polymer solutions keeps flowing and pulling uh, the rest of the polymer which is in the melt. So it's basically called a self-pouring fluid, uh, and this is the so-called viscoelastic properties that you have for polymer melts. Okay. So with that short introduction and in this strange video, let me start with the actual part of the class. And so today we will be talking about uh, the so-called ideal polymer chain, which is a random walk model of the polymer chain. So now in physics, what you okay, so in the last class, basically, I also talked about a very large class of polymers and which can have very unusual properties. Now, I mean, so I essentially introduced a very large different kinds of polymers which can have very different properties. And of course, as a physicist, you don't want to study all of them as an individual case because there would be so many properties, so much information, it would be difficult to register all of it. Instead, what you do is start with a very simple model. It is quite akin to when you study Newton's equation of motion. You say that let's take a small point particle, a ball which can be modeled by a point particle, and you throw it, suppose in the air, and the air doesn't have any friction. And let's figure out, solve Newton's equation of motion and figure out where the ball, so how far the ball goes if it has been thrown with velocity v0. Now you know that ball is not a point particle, the air has viscous friction, and so on and so forth, and there could be turbulence as it goes through the air. But you always start with that, and to study more interesting properties, you add complications to it. So that is the spirit of the discussion of the ideal polymer chain model. It is an idealization, and with this idealization, we can exactly analytically get some answers about the size or the spread of the polymer chain. And while we know that some of the assumptions made will not be correct, but this is a very good starting point, and from there we keep on adding corrections to it and get to the more realistic polymer models and its properties. And of course, you keep on doing that. You can add different architectures, talk about different networks and copolymers and so on and so forth. But the first class always discusses the ideal polymer chain model. As I said, this is the first and simplest model. It is also in the continuum limit called the Gaussian chain model. So what is the basic input to the model? It says it basically discusses the possible conformation and estimate of the size of a single polymer chain. A single polymer chain, when you're looking at a polymer chain in a single and it is undergoing Brownian motion in a solvent and taking all possible conformations, the picture you should have in mind is that you have a single polymer chain dispersed in a solvent and it is in the dilute regime. Okay. The other assumption is that it's a fully flexible polymer chain. So here is a schematic of the so-called ideal polymer chain. And this is one monomer. And this is the second monomer. And this is bond R1 denoted by small r1. And this is the second bond R2 connecting monomer number 2 and 3. And similarly, you have R3 and R4 and R5 and R6, right? Up till with n plus 1 monomers, such that you have n bonds. Now, the basic assumption, there are two basic assumptions in this ideal polymer chain model, also called the freely jointed chain. So it says that each bond vector Ri, and the next bond vector Ri plus 1, say R1 and R2. Now, R2 can take any angle with respect to R1. So each bond vector Ri can point in any random direction. It can even so R2 can even point along minus R1, if the case may be, or R2 might be exactly along the direction of R1 as well. So each bond vector R1 can point in any random direction independent of Ri minus 1 or Ri plus 1. So similarly, if you take R3, this is Ri minus 1 and this would be Ri plus 1, and R3 can take any direction independent of the direction of R2 and R4. So is this perfectly correct? Can R2 be exactly equal to minus R1 so that the third monomer will fall exactly on top of R1? No, of course not. It is not completely correct. But as I said right at the beginning of the class, that corrections can always be introduced as prefactors to the results obtained. Right? Uh, so in this, there is another inherent assumption. It basically assumes that individual monomers, so these spheres, you call them individual monomers or beads if you like, because as we shall discuss later, this could also be effective monomers. But at the moment, just consider them to be individual monomers in a model. The individual monomers do not repel each other. That is, they can sit on top of each other. Basically considering them point particles practically. What does that mean? It means that we are ignoring the excluded volume interaction between the monomers. What is excluded volume interaction? It says that each monomer, the bunch of atoms which constitute a monomer, uh, they basically occupy some finite volume in space, and they will not allow the atoms from other monomers to sit on top of each other. Right? So some volume is excluded, is not accessible to the other monomers. So if one particular monomer is sitting there and occupying a volume, so that volume is excluded to the rest of the monomers of the chain. So that is excluded volume. And basically, the Gaussian chain model or the ideal chain model is ignoring excluded volume interactions. What are the consequences? The consequences are that the bonds can cross each other. So there is nothing which prevents. So these are point particles. The monomers are considered to be point particles. There is nothing which prevents a polymer chain to cross itself. Why and how? So suppose this was a schematic representation of a polymer chain, and suppose that this bond was behind the screen. Suppose Z direction is the vector pointing into the screen, and suppose that this bond was behind in the negative uh, into the screen, right? And a normal, if you have a real polymer, basically it's possible that this bond cannot cross this bond on top, right? It would be hindered by the presence of other monomers, which will not allow it to pass through each other. But in the ideal polymer chain model, you have basically point particles as monomers, and the bonds can cross. So this is why it is called the ideal polymer chain. So all possible conformations are allowed in 3D as long as the distance between the monomers is a fixed distance, suppose L. And you could say that the vectors essentially do a random walk in 3D space, as opposed to a real polymer chain, as we have discussed in the schematic diagram. So this is not the actual case. So that's why I mentioned as opposed to a real polymer chain with excluded volume interactions incorporated. And when you look at the conformations of a polymer chain with excluded volume interaction incorporated, you would call them a self-avoiding random walk. Whereas this is just a simple random walk in 3D space, right? Okay. So as you saw, basically you have this point part monomers, and each bond vector of length L can basically point in any direction independent of the previous bond vectors Ri or Ri plus 1, and hence it is also called the freely jointed. Jointed means any, it can take any joint. So if this is a particular bond and this is the second bond, the joint is like free. It can point in any direction, hence a freely jointed polymer chain model. And the first question we ask is how do we calculate, or what do we can we say about the size or spread of the polymer chain? To that end, what we could do is calculate the end-to-end vector Rn. So suppose this is a polymer chain. So each of these are vectors, and there are many more vectors here. And the polymer ends here. So this is the last monomer, n plus 1th monomer, if you like, with n bonds. So then the vector joining this point to this point is the vector Rn, right? Now, this polymer can take various conformations because each of the monomers can move as long as they maintain the constraint of the bond length, right? So if you take an ensemble average, suppose you have various copies of this polymer chain, which constitutes an ensemble. So it's the representation of many equivalent polymer chains. uh, uh, or suppose if you take a time average, suppose you look at this polymer chain and see it as it evolves, as its conformations evolves with time as the monomers move around, right? And in statistical physics, the fourth year students would know that in equilibrium, time average equal to the ensemble average. But anyway, so whether you take a time average or an ensemble average, and that will give you the statistically averaged end-to-end distance mean. So mean. So because the polymer is going to keep changing its conformations, it does not make sense to talk about a particular end-to-end distance. Instead, you want the statistical mean, the average quantity of the end-to-end distance, right? But if you take the statistical average, right, um, so you would see that this mean quantity Rn vector mean statistical average would be 0. And why would that be 0? Because essentially if you are taking a time average and that's equivalent to taking an ensemble average at different instances in time, this vector would point in different directions, right? Because as the polymer changes conformations, at some point it would be pointing in this direction, and this monomer could move in at this point at a later point in time, and then the Rn would be in this direction, and at some much later point would be in this direction. And so basically all directions would be equally probable. And if you take the vector sum of all the Rn vectors over a long time, you would essentially get 0. So if you take R end-to-end distance and the statistical average of it, basically it does not give you any useful information about uh, the spread of the chain because you get it 0. It basically says that the end-to-end vector can point in any possible direction. But if you want uh, an idea about spread, uh, it is better to rather look at Rn. Rn is the end-to-end vector square, so it will be a positive quantity, so that if you are, it would be a positive quantity and a scalar. Here, basically, it was a vector sum and it became 0 on an average. But now there's a positive scalar quantity, it can't become average, and if you get its statistical mean, it will give you some idea about the spread of the polymer chain. So let's try to do that. And so suppose this is Rn vector, and so this is R, right? So it's supposed to be Rn actually. R here I've written R equal to end-to-end vectors, where Ri are bond vectors. Then R vector can be written as R1 vector plus R2 vector plus R3 vector plus R4 vector. And if you vectorially sum it up, you get the R vector. Okay. So R vector dot R vector, and then there is the statistical mean. So the ensemble average or the time average, doesn't matter, they're equivalent. Can be written as, so here we write R vector as sum of the individual bond vectors dot product with I goes from 1 to n, since there are n bond vectors. J is the dummy index again, j equal to 1 to n into Rj. So this is n to n, one n to n vector, this is n to n vector, and then this is a dot product. So this has n terms, so this has n terms, this has n terms. So the dot product would have n square terms. How is the pricing? Right? So basically you can write this as all possible values of Ri, I equal to 1 to n, into all possible values of Rj, j goes from 1 to n. So this is again n. So basically what you have done is this R1, R2, R3, R4 into R1, R2, R3, R4. So R1 dot R1 into R1 dot R2 into R1 dot R3 into R1 dot R1 into R2 into R3. So all possible products, and that's what this term means. And now there's a dot product. So basically taking its amplitude, where L is equal to the bond length, can be written as angle between bond vector I and bond vector J, right? And then you have the ensemble average. So I have focused, I have marked it in pink, ensemble average. So after calculating this, you have to do the ensemble average. Now, when I equal to j, cos theta ij, so I and j, you are talking about the same bond vector. So cos theta ij will be 1 because theta ij will be 0. So, so basically R1 square plus R2 square plus R3 square plus R4 square and so on and so forth. So n terms for n bonds. But when I is not equal to j, so r1 dot r2 or r2 dot r3 or r3 dot r4 or r1 dot r3, such terms basically, since each, so I can point in any direction and j can point in any direction, so this mean, the statistical mean of the cos theta ij would be 0. So out of the n squared terms, you would have n terms which would contribute L square, but the rest of them, when you take a statistical mean of it, because theta can be any direction and each direction does not have an energy cost, so this Boltzmann factor e to the power energy minus beta energy by qdt, it's basically 1. So all conformations are equally probable. What you get is essentially, if you average over all cos theta ij, because all are equally probable, you get 0, right? So n square minus n terms, all possible when I and j are unequal, I is not equal to j. You get this equal to 0, and you have n terms which are non-zero, right? So I have mentioned this here. So basically, what you have is Rn dot Rn average. There are n terms, and each term is of size L square, is of magnitude L square, which is the bond length. And all of this is basically well described in the book on polymer physics by Rubinstein and Paul B, chapter 2, section 2.2. And this is absolutely taken from there. Uh, okay, so you basically get a mean, a statistical mean of the square of the end-to-end vector, right? And call that Rn. So Rn is equal to square root of this mean of the square of the end-to-end vector. So that's the distance again, right? Because this is distance square. And what you see is that the end-to-end distance goes as square root of n, where n is the number of vectors, the number of bonds in the polymer chain, right? And furthermore, basically, yeah, so this is of see this is the error. So this is of this is a length, and this should not be L square, but instead it should be L. So it should be root n. So this is correct. R square average is NL square. So R square goes as n, but Rn goes as root n. So this square and this square is wrong. So what is the basic message? Remember that this is a statistically averaged mean quantity. The, the measure of the spread of the chain, which can be given by the end-to-end vector, statistically average, goes as n to the power half, which is true for an ideal chain. Okay. Okay. So next, so this was called a freely jointed chain model, where all possible joints are allowed, all possible angles are allowed. Now, next, actually, we'll very briefly touch upon the freely rotating chain model. So in the freely rotating chain model, what you have is, suppose that this is a bond, okay, and this is the next bond. So suppose this is I and this is I bond vector I plus 1, then it can rotate about the axis, but its angle of this bond and the next bond is fixed at theta. Okay, some fixed value. But about this bond, while maintaining theta, it can basically point in all possible directions. Okay, so it's basically, it can go like this, but this angle, so with respect to this, the angle theta has to be maintained. Okay, so suppose this is vector ri, then ri can be like this, or in like this, or just behind in the screen, into the screen. So angle theta has to be maintained. This is Ri plus 1. This is bond vector Ri plus 2, and with respect to I plus 1, it again maintains an angle of theta while rotating. Now, if this angle was basically, if this vector was in this direction, then basically Ri plus 2 can take all possible angles uh, about this line. On the other hand, if I plus 1 pointed in this direction, then I plus 2 could possibly rotate, maintaining an angle theta about this direction. So hence, so I mean, so since this can rotate in all possible directions, correspondingly, this vector shall rotate, maintaining an angle of theta with whatever is the direction of I plus 1. Hence, I have drawn this and this, which are equivalent. So in terms of the calculations, all that you had to do was essentially, so up till this step, basically this is here, it's really the same, but now you have a cos theta ij, and between Ri and Ri plus 1, when you take the ensemble average, you won't get 0. Instead, you will get a fixed value of cos theta. And if you take I Ri dot Rj, where j is suppose I plus 2 or I plus 3, then basically j can be written. So j, if j is I plus 3, then this r vector then this r vector I plus 3 can be written in terms of I plus 2 by taking an appropriate cos theta, and r2 can r I plus 2 can be written in terms of I plus 1, and Ri plus 1 can be written in terms of I by taking suitable dot products. So as a consequence, so basically what you will have in the dot product, as j and I differ, L square will be cos theta j minus I, the modulus sign, right? So the modulus sign, because j can be greater than I or less than I. And this L square cos theta j minus I can be written as, the L square is intact, I write it as an exponential and log. So log and exponential is the same as cos theta j minus I. And this in turn is just a simple algebraic manipulation. So basically cos theta to the power L minus j modulus, that basically comes here because there's a log and you can take it out. And in turn, one can write this as j minus I, and this ln cos theta you're writing as 1 upon ln cos theta, introducing a minus sign here and a minus sign here. And this in turn can be written as L square exponential j minus I, which is intact. I introduced a minus sign in terms of SP. So writing it in exponential allows you to do some algebra in terms of a GP series and AP series and so on and so forth. As a consequence, the end-to-end distance, which was NL square for an ideal chain, comes with a prefactor of 1 plus cos theta and 1 minus cos theta, where theta, remember, is this angle. So when theta is 0, it is pointing exactly along the, so Ri plus 1 is pointing exactly along Ri. In ideally, in the ideal chain, basically this theta could take all possible directions, but now there is a limitation. Theta is fixed for the freely rotating chain. Now remember, so when theta is less than 90 degree, basically you're looking at small deviations away from the straight line along the, so theta is relatively small. Then basically this is something which is greater than 1. So basically end-to-end distance square mean You have NL square, and this is a number which is greater than 1. Right, so this is more like a semi-flexible chain. Not all possible angles are allowed, and there are some restrictions in the angle for which basically there's a tendency for a polymer chain to point along the same direction for quite some length of time. We shall come back to this. Semi-flexible chain means there's a finite uh, bending, there's a cost for bending energy. You can't bend the chain freely. Freely jointed chain, there was no cost for bending, right? So, and as a consequence, this for a freely rotating chain, the end-to-end distance is larger than the end-to-end distance of a freely jointed chain. But REE, it maintains the n to the half factor, though the prefactor has changed. Uh, Remember, in the freely rotating chain as well, chain crossing is allowed, excluded volume interactions are neglected. Okay, so so at least we talked about an ideal chain and a freely jointed chain. Now the next question we're going to ask is okay, but we know what is the mean size, a mean statistically mean size of the chain for the freely jointed chain, for the ideal chain, say, right? But what about the distribution of Rn? Okay. Okay, so just I think I'll take a break and then continue recording in some time.